All right, we're about to start the 140 Expo Hall talk. The topic is computing resilience. I'm Rob Chappell. I'm from Microsoft Azure. And one of the things that I do at Microsoft is I look after the health and well-being of our millions of server nodes. Interestingly, before I came to Microsoft, I spent 20 years architecting high-volume product CPUs. So when it comes to computing resilience, I kind of have a dual perspective on it. Now I'm a silicon customer, but most of my career I was a silicon provider designing for computer resilience. So resilience to what? Well, it's silent data corruption. So the interest in CPU silent data corruption has grown rapidly over the past few years. There have been a number of publications, and starting from the first two, these were from Meta and from Google early last year, that kind of put a spotlight on this problem of silent data corruption in the cloud. The last article is actually kind of more intriguing because it's a New York Times article. So that meant that the topic transitioned from technical professionals talking to each other about it to actually some mainstream media coverage. In addition to the publications, there's been a number of panels, including at the OCP Summit last year, also at the International Symposium of Computer Architecture, or ISCA, that's the flagship CPU architecture conference, also at the Design Automation Conference, where I was fortunate enough to be on that panel. And then we have another one on Thursday morning that's sponsored by our workstream. So there's a lot of interest. Why? Is this some new problem that's come to disrupt the cloud? Well, not really. It's actually a decades-old problem. Very early on, it was discovered that digital circuits are subject to what we call bit flips from a variety of causes. And this is silent data corruption. You either store or compute a value, and you don't get what you're expecting when you look at the answer. And some of the reasons why that can happen are defects. So this is a manufacturing error that escapes manufacturing time testing into the wild, or it can be a latent defect that actually manifests in production life. It can be a marginality, which is a process variation conspiring with environmental conditions to take a circuit outside of its operating margins and thereby cause a corruption. It could be wear-out effects like electromigration or oxide wear-out that actually cause the circuit to degrade over time and then fail before its designed end of life. All of these things are what we would call hard errors, where there's actually a physical problem with the part that will repeat, and it can produce silent data corruption. Now, when you're architecting for these things, you also have to worry about soft errors. So this is where the part is not actually, physically defective, but you are subject to particle strikes that can cause charge to move and cause the bit to flip unexpectedly. So, the realization that these things were possible led to decades of work, dating back to at least the 1950s, in computing resilience. So these are things like error-correcting codes and manufacturing testing and design for test and hardening devices and using redundant computation. Like all of this stuff happened for decades, and generation over generation, when we're designing new CPUs, we're designing for resilience. So it sounds like it's sort of a solved problem. So what happened? Why are we talking about it again? Well, what happened is scale, specifically cloud scale. So when I talk about cloud scale, immediately you're probably thinking data centers. So the biggest cloud providers have hundreds of data centers all over the world, millions or even tens of millions of server nodes. I like this picture from our data center in Virginia because you can see that there are multiple phases of the construction. So it's not just more data centers, it's also building onto existing data centers, getting capacity wherever we can get it. Beyond that, here's my obligatory Moore's Law slide. The scale of integration has also been increasing. So there are more servers going in, and each one of those servers is more dense. So it's kind of hard to read, but the top of this is 50 billion transistors, and that's 2 years old. So increasing scale in servers, increasing scale of servers, and the last dimension I want to talk about is problems. This graph is from a benchmark from Death Star Bench that is trying to model an e-commerce application. And you can see that there are a lot of boxes. So then this isn't even the biggest type of problem. So you have a lot of different servers talking to each other together, working on a single problem. And so the possibility of a corruption affecting that entire problem becomes larger because of that. So the bottom line is that hyperscaler clouds have the colossal scale to observe ultra-rare events, including SDC, despite all of the stuff that I talked about in the previous slide that is working to prevent it. Okay, so what's so bad about SDC? Well, we used to think as architects, this was the worst thing that could possibly happen. It's a unique challenge, and what makes it unique is that the S stands for silent. You don't know that it's happening, kind of by definition. Events are either unnoticed, or if you get lucky, you have an anomalous behavior, like a system crash or an error message or something. The problem is, even when you get that, it almost always looks like a software problem. And it's only after months of debug ruling out every other possible thing that you might conclude, I've got nothing left, so it must be silent data corruption coming from the hardware. It's also impossible to measure, again, by virtue of being silent. So you don't actually know how often it's happening. What we can do is we can screen for bad parts. So we run specialized tests that have a known good answer. We compare against those answers, and if we get a mismatch, well, then we know that the computation was incorrect. And then based on that, we can project the number of bad parts we have, and we can try to project the number of incidents that we have. As I mentioned previously, causes can actually emerge after parts enter service in the data center. So it's the model of you're buying a tested part that is, definitely good and then will operate correctly for its lifetime. It just doesn't work at scale. We have to account for the fact that we're going to find bad parts that emerge after they go into production. So we need to manage that silicon lifetime with periodic testing and with directed testing and models. Last thing, if it wasn't beaten into your head this morning in all the keynotes, we have a problem in growing scale and energy and our ability to sustain that growth. And so a solution like redundancy, which is what you have when like a mission critical system like your self-driving car or something, you can't scale that to the entire cloud. That's like tripling the size of the cloud. It's just not practical. So what are we doing about it? Well, this is OCP, and the answer is collaboration. As you heard in a couple of the keynotes this morning, Microsoft, along with other major CSPs and silicon providers, have gotten together and we founded the Server Component Resilience Workstream. Our goals, first and foremost, we want to get industry and academic awareness of this problem. We want to get engagement and motivate people to do something about it. That can include, obviously developing new solutions, but also investing things like silicon area into these problems for the cloud, where in some other environments, maybe don't value resilience as much because, who cares if your phone reboots once a year? We can't afford to take that position. Based on that, we expect that we'll get solutions and we'll get best practices to prevent and detect SDC. One of the toughest things is, let's say you have these new solutions and new ideas. How do you know if they're any good? Well, you need metrics to try to project what the incidence of SDC is, and you need a way to judge the effectiveness of a new screen. So one of the tracks that we have in our work stream that we're starting is talking about metrics. How do we standardize these metrics so we can talk to each other about how bad the problem is, and then realize if we're doing something right and we're making a positive impact. And the last thing that we need is standardized methods for hyperscale screen development. So a lot of the improvements will come from experimentation, but how do you do experimentation if you need extreme scale and you can only find bad parts to experiment on when you have extreme scale? Well, we need a way to enable that. And so what the work stream is talking about doing is trying to find a way to have researchers package up tests and be able to run them in a hyperscale environment against known bad parts to see what they can see which defects they can find, see how fast they can find them, and thereby judge the effectiveness of screen development. So if you're interested in finding out more, we have a mini panel on Thursday. It's Thursday morning at 9:05. The title is Silent Data Corruption, Need for Broader Academic and Industry Engagement. Some of my colleagues from the workstream will be there on that panel. Keep an eye out for the new workstream's landing page. We don't have one currently, but it will show up under the server project. And if you're interested in talking to me more, I'll be at the Microsoft booth periodically throughout the day, or you can visit any of the other companies that are participating. Okay. Thank you.